Okay, and welcome back to the fifth and final installment of the Delaware Tech Physics 111 Exam 2 Preparation and Practice Exam covering forces and energy. In this video, we're going to cover various types of energies like kinetic energy, potential energy, specifically gravitational potential energy, mechanical energy, and non-mechanical energy. Let's look at the problem. Number 14. A 50-kilogram boulder falls from the top of a high cliff. When the boulder is still 62 meters above the ground, it is traveling at a speed of 15 meters per second. So the boulder has already fallen at some point in time. It's still 62 meters above the ground, and it has a speed of 15 meters per second. The boulder eventually lands and stops intact on a sand pile 3 meters above the ground level. So it's not landing all the way at the bottom, it's landing at 3 meters above that ground. And you're given a value of G equals 9.8 meters per second squared. Part A says, what is the kinetic energy at the 62 meter high position? And part B says, what is the gravitational potential energy at that same 62 meter high position? So let's draw a quick diagram that explains what's going on. We have this cliff, a boulder initially up at the top of the cliff falls, and at some moment in time, the boulder is in the air. It is still 62 meters above the ground, so that is our height, and it is moving at 15 meters per second. That is our speed. And we're asked to calculate kinetic energy and gravitational potential energy. Well, kinetic energy is 1/2 mv squared, 1/2 times the mass times the speed squared. Well, we know the mass of the boulder is given in the top in the question. It's 50 kilograms. And we know the speed is 15 meters per second, and we have to square just the speed. If you want to square that in advance, that would be 225, and since we're squaring both the number and the units, it's 225 meters squared per second squared, and then you multiply that times 50 and times 1/2, and your final value is 5,625 kilogram meters square per second squared, but that's just joule. And you don't need to worry about working out the units. If it's a form of energy, it is always going to be in joules. If it's work or it's any form of energy, your answer will be in joules. Part B, what is the gravitational potential energy? Well, gravitational potential energy is mass times G times H. And you'll notice when we're calculating kinetic energy, we don't care about the height. The height is unimportant. What's really important is the speed and the mass. But for gravitational potential energy, what's important is the height and the mass. And we're going to throw those numbers in. Again, we have a 50-kilogram boulder, but now we're multiplying it by G. G is 9.8 meters per second squared. And our height at that moment in time is 62 meters. Again, we plug this into our calculator, and we get a value of 30,380. And you see the units are kilogram, meters per second squared times another meter. But we already know that those are equal to joules. So you're just going to write joules. Gravitational potential energy is a form of energy, so it's going to be measured in joules. We look at part C. C says, what is the kinetic energy after the boulder hits the sand? Well, remember, kinetic energy, as always, equals 1/2 mass times speed squared. Well, it doesn't matter what the mass is. The speed, once it hits, is 0 meters per second. So it has no speed, therefore it has no kinetic energy. So that's going to be 0 joules. Part D says, what is the gravitational potential energy after it hits the sand? As always, gravitational potential energy is equal to mgh. We know m is 50 kilograms. We know g is 9.8 meters per second squared. And we know the new h is 3 meters high. Remember, it doesn't come to ground level. If it came to ground level, that would be 0 meters high, and therefore the gravitational potential energy would be exactly 0 joules. But it's 3 meters high, so we have to plug these three numbers into our calculation and work out our value, which is 1,470 kilogram meter squared per second squared, which we know is a joule, and that's our answer. Part E says, what is the mechanical energy at the 62 meter high position? Well, mechanical energy is merely the sum of the kinetic energy at that moment in time plus all potential energy at that moment in time, but the only potential energy we're dealing with here is gravitational potential energy. So we just add up those two energies. Let's scroll back and see what we have. We have a kinetic energy of 5625 joules, and we have a gravitational potential energy of 30,380 joules. So we just add these together. And the sum of those two is 36,005 joules. That is the mechanical energy at the moment in time when the boulder is still 62 meters high, 62 meters above ground level. Part F is asking, what is the mechanical energy after the boulder hits the sand? Remember, it's hitting the sand, it's stopping at 3 meters above ground level. So we have the same formula for mechanical energy. It's equal to the kinetic energy at that moment plus the gravitational potential energy at that moment. Well, if it's stopped, we already know it has 0 joules of kinetic energy, and we've calculated the gravitational potential energy at 3 meters high for this object of 1,470 joules. Well, when you add up 0 joules and 1,470 joules, we get a new mechanical energy of 1,470 joules. So we started with a very high amount of mechanical energy, at least midway through the fall, and after impact, it went down to 1,470 joules. This tells us that we lost a lot of energy in the form of mechanical energy, so it must have been turned into non-mechanical energy. Now, part G says, how did the kinetic energy change during this time? It changed a great deal. If we look at the value, we know the kinetic energy was previously 5,625 joules to stopping, so that's 0 joules. And why did it decrease? Because it stopped. In fact, during the fall itself, the boulder was gaining kinetic energy because it was gaining speed, but when it suddenly stopped at the end, it loses all speed, so it loses all kinetic energy. All right, part H. How did the gravitational potential energy change during this time, and why? Well, in this case, we have the boulder falling, so it's going to be dropping in height and therefore dropping in gravitational potential energy as well. Well, we already calculated these values. We know that in the middle of the fall, the gravitational potential energy was 30,380 joules, and that decreased when it dropped to the level of only 3 meters high, from 62 meters to 3 meters high, and at that point, the gravitational potential energy was 1,470 joules. Again, we have a large decrease. So why did it drop? because the height decreased. Part I says, how did the mechanical energy change during this time and why? Well, we calculated mechanical energy while it was falling and after it hit in parts E and F. So the mechanical energy decreased from 36,005 joules to 1,470 joules. So we have a decrease in mechanical energy. And why did we have a decrease in mechanical energy? Because both the kinetic energy and the potential energy, specifically the gravitational potential energy, decreased. How did non-mechanical energy change during this time and why? Well, if the mechanical energy decreased, and we know that that energy had to go somewhere, well, then the non-mechanical energy must have increased. Just to remind ourselves what the non-mechanical energy is, this is internal energy. If you said thermal energy, that would be fine. Sound energy, otherwise known as acoustic energy, and deformation energy, technically known as elastic strain energy. Don't confuse that with elastic potential energy. So those are the three energies. Well, what are these? Well, this is transferring heat from one object to another and making the molecules vibrate more, and all the various particles, including subatomic particles, vibrate more with more energy inside whatever is gaining that energy. Sound energy is from the sound. When the boulder hits, it's going to make a sound that will create a form of energy that travels through the air and through the rock as sound vibrations. And then the rock itself might break, or the ground below it might break or be deformed. That's deformation energy. Well, if the mechanical energy went down, then the non-mechanical energy must have increased. The energy had to go somewhere. It went to the various forms of non-mechanical energy. How did the total energy change during this time and why? Well, the implication of the previous question is that when we lost mechanical energy, we gained non-mechanical energy. Well, that is only true because total energy is conserved. That means it never changes. The law of conservation of energy tells us that the total energy is constant as long as we count all the different forms of energy that have moved around and gone from one object to another. Energy is conserved. And with that, we'll stop here.